What we're going to do here is look at example 7 from the lecture notes. As I mentioned before, this example does not appear in the notes you received in the mail. Rather, you're going to have to download a copy of this from the PDF link that's there on the lecture page on the blog. But what we have here is a problem which is pictured in figure 423 of the textbook. Got two blocks of mass M1 and M2. M1 is connected back to ground with a spring of stiffness K, and the M2 block is connected back to M1 through the cable pulley system that is shown. I think it probably says in the textbook that we can ignore the mass of the pulleys. Along the way, we've got X here measuring the position of block 1, which is measured from the unstretched state. I'm going to introduce a temporary coordinate here of Y, which measures the position of mass M2 from the unstretched state. In addition to that, I'm going to be talking about the position of the middle of the pulley. Here on the top, I'm going to call that S1, and then the position of the block from that pulley here and call that S2. We'll use those later on as step 3 when we're looking at the kinematics. First step is FBDs. We'll draw free body diagrams of blocks M1 and M2. So if M1 is this block, M2 is this one. I'll also throw in fact, let's put the pulley along with that one. Okay, and this pulley here, I'll show that one to help us understand how the tensions are in the cables. So this block M1 has a normal force of N. It's got a weight here of M1G. It's got a spring force over here on the left-hand side. The force is K times X. X is measured from the unstretched state. X is measured positively to the right. When X is plus, then the spring here on the left is in tension. It's going to pull. I draw the arrow to the left. We have a tension force here of T. Let's call it T1. T1. This pulley, we've got T1. T1 like this. I'm sorry, I'll call it T2 just to be different. Call that T2 like that. M2G down like that. Okay, so if I look at the free body diagram 1, summing forces in X, with this done I have minus Kx. I've got two tension forces of T1, so that's 2T1 is equal then to M1 X double dot. Free body diagram for 2. Recall that I defined this variable of Y. It's measured positively downward, so that defines the sign convention for the forces. So T2 there is up, which is a minus, plus M2G, and that's equal to M2 Y double dot, like that. And then if I look at the pulley, which I'll call 3, since the pulley has negligible mass means I do a moment, let's say, about O. It's equal to a 0 because we can neglect the mass. It's an ideal pulley. And basically this is going to give for us that T1 is equal to T2. Had we decided that the mass of the pulley was important, then we'd have to go through the usual Euler equation to find the relationship between T1 and T through 2, which would involve like the mass moment of inertia of the pulley. So basically we have here that the first equation gives us that T1 is equal to M1 X double dot plus Kx divided by 2. And equation 2 says that T2 is equal to m2 g minus y double dot, like that. If T1 equal to T2 from here, we see that our equation of motion, I should say, is 1/2 m1 x double dot plus kx, and that's equal to mg minus y double dot, like that. So that looks like we're getting close to what our equation of motion has to be. We've got 1. We have 1 degree of freedom. The catch here is, of course, we've got a y and we have x's on this side. Okay, so we have to use our step 3, our kinematics. So this was step 1. I didn't leave room for step 2. That's Newton. Step 3, kinematics. We go back to our cable pulley equations, which you've seen in a couple courses now. So if we look at the length of the cable, the length of that cable is made up by this length here, which is an S1. We have another length S1. We have a constant here, the wrap of the cable around there. I don't know what it is. We weren't given that dimension. But the important thing is that it's a constant. This length here is S2. Then we have another constant wrap length there, which we don't know. We really don't care. So as I add them up, I get S1 plus S1 plus a constant called C. It's C1 to represent this one. And then I have another constant, C2, which is this wrap there, plus S2. And that's equal to the length of the cable, which is a constant. I do a time derivative of that. In fact, 2 of them. What I'll get is 2S1 double dot plus S2 double dot is a 0. So it says here that S2 double dot is equal to minus 2S1 double dot. Let's be very careful we don't lose any signs along the way. That minus sign is very important. So what I could say here by looking at the picture is that from the picture that x double dot is a minus S1 double dot. Why is that? Well, the fact that they have the same magnitude is important, or easy to see, I should say. The displacement of the center of the pulley is the same as the displacement of the block in magnitude, except they're measured the opposite way. And S2 double dot and Y double dot are one and the same in both magnitude and sign, like that. Okay, so these three together say that our kinematics are that Y double dot is equal to S2 double dot, S2 double dot is equal to minus 2S1 double dot, so that's going to be equal to get this right here, minus x double dot. So minus and a minus now make that a plus. Does that make sense? Well, let's look and see. The plus sign means that if x increases, then so does y, and I think it makes sense as the block moves to the right, then block 2 moves down, and that's both positive x and positive y. So that's good. So that we can take this kinematics equation, substitute it into our equation of motion from the step above, and that's going to give us our equation of motion for our system. So this is going to be 1/2 m1 x double dot plus 1/2 kx is equal to mg minus my double dot, so that's a 2x double dot, like that. And therefore what we have when we bring things together is we're going to have a 2 here on the left side adding to a half. So it's a 5/2. Oops, I can't combine that. I was very messy here on my notation. The second equation here is an m2. So this has a subscript of m2. And I have an m2 here and m2 there. So what I have is 1/2 m1 plus a 2m2 x double dot plus 1/2 kx is equal to m2g. That gives us our equation of motion as desired in terms of x. Recall that x was measured from the unstretched state. That's how we were able to come up with the forces. The second part of this question says, what if we want to write it in terms of something else? And that is going to be an equilibrium state. Equilibrium state basically says that the accelerations and velocities are zero. So it says that 1/2 k, I'll call it x naught, is equal to m2g. So therefore our equilibrium state then is equal to 2 m2g divided by the stiffness of that spring connected to block x1. This is the equilibrium deformation of the spring. The question asked is for z. Z, which is defined to be the difference between x and x naught. Basically it says if you brought this, let the thing go at a position where it could be in equilibrium, then z is a 0. Okay, so any motion about that equilibrium state of x naught is called z. In other words, what we have therefore is that if this is true, then every place we have an x, we're going to put a z plus x naught. Every place we have an x double dot, we'll put a z double dot. X naught is a constant. So in our equation we have 1/2 m1 plus 2m2 times z double dot plus 1/2 kx, and x is z plus x naught, and that's equal to m2g. This here is 1/2 kz plus 1/2 kx naught. Up here x naught was equal to this. This is 2 mg over k. So we see that the k's cancel out, the 2 cancels out with the half, and what we have on the right hand side will cancel out with what's left there. What's the point? Well, the point is by writing it in terms of motion about the equilibrium state, it looks a lot like it did before, except for one major difference, and that is gravitational force doesn't appear. In other words, we have a 0 there on the right hand side. So the point here is that most problems where weight comes into the picture, if you measure the motion from the equilibrium state, then weight will disappear. That constant term on the right-hand side is a zero. Stated in different words, the inhomogeneous equation of motion for x becomes a homogeneous equation in z.